Okay, so good evening, everybody. We are meeting after a break. In between, you have learned from Dr. Kanu Barik about various characterization techniques that can be utilized to characterize the material. Okay, so basically, as far as my portion is concerned, we are left with two topics. One of it is on phase transitions, and the other is in general synthesis of material. So will try to cover as much as I can. I'll try to leave some of the things which I would feel that you can understand on your own. But you're most welcome to come back to me, mail me if you have any doubt. And let's try to finish these two topics today. Phase transitions is an important branch of materials chemistry that has implications in terms of properties. Because as all of us were discussing, and we have been talking about it since the very first class, that the property of the material depends upon its structure, defects, and composition. Now, since structure is a very important part, it plays a very important role in determining the properties of the material. If the same material has the capability to exist in two or three different structures, it shall definitely alter the property. So it becomes very important to understand about various crystalline phases of the same material and in turn the phase transitions. Okay, so basically, what is phase transition? As the name suggests, if any material is capable of existing in more than one crystalline form, then when it transforms from one form to another, it is called a phase transition. And the phase transition can happen in response to the temperature, in response to the pressure. Sometimes the phase change can also happen in response to the composition, which is most of the time what solid state chemists do. But that also we call as that the material has gone phase transition. But since the composition changes, so in stricter terms, it is not called as phase transition. So thus repeating, change of a material from one crystalline form to another crystalline form in response to change in temperature or pressure is called phase transition. So what are polymorphs? The two or three different polymorphs of this compound which is having the same composition. When I call that as compound, obviously the composition is fixed. So two or more different crystalline form of the same material are called polymorphs. The examples are when we were talking about structure property relationship, if you recall, we talked about barium titanate as a ferroelectric material. The barium titanate can exist depending on the temperature in cubic perovskite form, in tetragonal is the one which is ferroelectric and has got high dielectric constant, then rhombohedral. So all these crystalline modifications which belong to barium titanate are called polymorphs. Similarly, your silica, SiO2, a very, very commonly occurring material. It exists in many polymorphs, many different crystalline forms, and their general names are quartz, cristobalite, as is mentioned here, tridymite, stishovite. All of these differ in how the SiO4 polyhedra are linked with each other. Okay, so how do we classify phase transition? So classification, as I said, is very important. Not just because we have to learn it; they exist. It is because they help us to let's say we have identified a new material which shows phase transition. Then, depending upon how the phase transition is happening, it is easier to club it with the material which are showing similar kind of mechanism, and thus it is easier to kind of predict its properties. And that is why the classification has importance in all the areas of sciences. I would not say chemistry or solid state chemistry or even biology and all that. So coming back, what are the different ways we can classify the transformation? First is on the basis of thermodynamics. Most of you, either you know about it or you would have read about it or at least you would have heard about it. Means a order of the phase transition. It is a first order phase transition or a second order. So that depends upon the thermodynamics of that particular phase transition. And this was given by Aaron Fest. The second thing is, what is the mechanism by which the phase transformation is happening? And with this method also, like the mechanism being followed on going from phase 1 to phase 2 also provides a method for classification of phase transition. And in thermodynamics, we say order of the transformation based on mechanism. And this classification was given by Berger. Based on mechanism, we can classify them as two types of phase transition: the reconstructive and the displacer. We'll study a little more about them. First one is reconstructive phase transition. So it doesn't take an Einstein to understand that. As the name suggests, reconstruct means you are breaking whatever is already existing and then you are reconstructing it. In other words, the transition occurs by breaking and then appropriate rejoining of bonds in the other phase. Okay. So I'll repeat. Reconstructive phase transition happen by breaking and reforming of the bonds. Okay, and because it involves bond breaking and reforming, so these processes are slow. So that is why reconstructive phase transitions, wherever they happen, are relatively slower. And because they involve the breaking and formation of bonds, they also involve energy. So reconstructive phase transition have got high activation energy. Also, because once you have broken the bond, and they can rejoin in whatever way they want. So it is not necessary that the polymorphs 1 and 2, between which the phase transition, that reconstructive phase transition is happening, they might or might not be symmetrically related to each other. Most of the time, there is no symmetry relationship between the polymorphs. Example is your graphite and diamond. So all of us know, we have been studying right from very early days in schools. So graphite, if you see here, is actually the sp2 carbon atoms linked together to form layers, and then those layers are linked together by van der Waals forces. Whereas in diamond, the carbon is sp3 hybridized and each carbon is linked to four other carbons. So this is a three-dimensional network. Graphite, on the other hand, is a two-dimensional linkages. So you have same carbon, but it is actually arranged in a different manner. It has different symmetry, and if you want to convert this graphite, which is a planet structure, to diamond, which is a three-dimensional linkages of the carbon, you need to break and form the bonds. So this is a reconstructive phase transition and it is slow. So all of you know that diamond is actually the metastable form of carbon at room temperature. So whatever diamond jewelry we have, it is stable only because diamond, once it is formed, it does not go to graphite. But otherwise, energetically, at room temperature, under ambient condition, graphite is the more stable form of carbon. Okay, coming back to our thing, one example was carbon. Graphite and the transition between graphite and diamond is a reconstructive phase. Second example is silica. Silica is SiO4 tetrahedra. But okay, so how these SiO4 tetrahedra are linked together, okay, in quartz, to cristobalite, to tridymite. Those SiO4 tetrahedra are intact, but the way they link with each other, that is different. So to convert quartz to cristobalite, I need to break these SiO4 linkages and join them in some other way. So there is involvement of breaking of bond, reforming of bond. It is a reconstructive phase transition. Coming to displacive phase transition, again, as the name suggests, displacive phase transition, the bonds are not broken, the bonds are simply displaced with respect to one another by small distance. Okay, and those distances are more or most of the time smaller as compared to internuclear distance. That is, during the transition, the movement of the bond that happens is even lesser than your internuclear distance. So, displacive phase transition involve simply the displacement of the bond and the atoms with respect to one another, and they do not involve any breakage or reformation of the band. Very obvious, since it does not involve any breakage or reformation, the displacive phase transition are faster. Time required to complete, it is basically happens on the order of time required for a phonon. What is a phonon? It's a lattice vibration. And because they are faster and they simply involve movement of bond, to most of the time activation energy is very low. And because again, as I said, it involves only the tilting of bond, there is a definite symmetry relationship between the two polymorphs which are linked together by displacive phase transition. Okay, an example is in case of SiO2, I told you in the previous slide, if you have to go from quartz to tridymite, you need to heat it. It is a reconstructive phase transition. But even in case of quartz, just by tilting of tetrahedra, we can transform between beta quartz and alpha quartz. And this is a displacive phase transition. So quartz to tridymite to cristobalite, reconstructive. Beta quartz, alpha tridymite, beta tridymite, alpha cristobalite, beta cristobalite, they are displacive phase transition. Just to make it a little more clear, you concentrate at a particular square which is formed like this. Okay, that's a bad drawing, but you can see this square here. Okay, now, and this entire structure is actually formed by linkages of these squares, right? Now, if I want to convert this structure A into either B or C or D, I will have to break and reform the bond. So conversion of A to B, A to C, A to D is the reconstructive phase transition. But if B has to go to C, as you can clearly see, it is simply the tilting of these squares. If C has to go to D, it is again the tilting of these squares. So B to C to D or in reverse direction is displacer. A to B, A to C, A to D reconstructive. Also, it is very clear, even if you do not know anything about symmetry, as a layman, you would be able to tell that the symmetry of the A is much different from B, C, and D, while there occurs to be a definite symmetry relationship between B, C, and D. Okay. Now, there is an interesting phase transition, again a displacer phase transition that happens in rock salt structure. And since it is interesting to talk about and understand, I thought I would include this. Okay, so what is your rock salt structure? Let's say if I'm talking about chlorine at the center, then the chlorine will occupy H center. If I'm talking about sodium at the corners, the sodium will occupy face center. Okay, so this is your rock salt cube. And in case of rock salt, the coordination number of each ion, whether it is Na or Cl, it is 6. Okay, now you just concentrate on this chlorine at the center. Its coordination number in rock salt structure is 6, which is actually sodium 4, sodium 6, sodium 7, sodium 3, sodium 5, and sodium 2. Now, what happens when you increase the temperature? The phase transition occurs from rock salt type structure to CaCl type structure. And CaCl is a primitive structure where the coordination number of your ion is 8. Okay. Now, how that happens is just to make you understand, just to visualize it. If along the body diagonal 1/8 of this rock salt structure, you compress it in this direction. Okay. it will be a formation of new cube which you can clearly understand, wherein you concentrate on this chlorine, and this chlorine is at the center, and the atoms sodium 8, 7, 4 and 3. 8, 7, 4 and 3 from the form the upper face, and 6, 5, 1 and 2 they form the lower face. So what happened is chlorine, which earlier had the coordination number of 6, now has the coordination number of 8. And the vice versa we can also imagine for sodium, because sodium and chlorine are interchangeable in rock salt structure. So what eventually we get is, once the coordination number of chlorine has converted from 6 to 8 via this particular mechanism, it has converted to cesium chloride structure, isn't it? Also, since this involves only the movement of bond, what has happened is atom number 8 and atom number 1, which were not in the first coordination sphere of chlorine. Okay, chlorine had only 6 atoms in its first coordination sphere. They have simply moved in the first coordination sphere of chlorine, increasing it from 6 to 8 and forming a regular cube, and promoting the phase transition from rock salt to the CaCl structure. Effect of pressure and temperature on phase transition. Temperature, what happens is, as you increase the temperature, barring very few exceptional cases, the materials expand. So when they expand, it is, even if you do not know the mathematical formula, it is very clear, and it is, easy to visualize that if the phase transition is happening on increasing the temperature, your high temperature phases will have more open structure because the material is expanding, and the atoms and ions, they will have lower coordination number. Okay, all right. The high temperature phases will be more disordered but more symmetric. So even though in terms of language disorder and symmetry are opposite, but here they mean completely different things. Okay, and we'll understand it a bit later. So high temperature phases are more open, they are more disordered, and they are more symmetric. Reverse in case of pressure. While temperature tries to expand the thing, the pressure tries to compress it. So when you're compressing and you're going, let's say a phase 1 is undergoing transition from phase 1 to phase 2 at high pressure, what happens is you're trying to compress it. So the high pressure phases will be more dense, and the atoms or the ions, they will have higher coordination number. Okay, they'll be more ordered, but they will be less symmetric, because you're not trying to compress it, it is trying to fit in as many atoms around it as possible, and in that case it might lose the symmetry. For example, for AB kind of compound, let's say NaCl, if you start from cesium chloride, the coordination number is 8. Increase the temperature, the material will get a rock salt structure. I hope you understand that. You're not children. That it's not that cesium chloride is converting to sodium chloride. The cesium chloride type of structure is converting to sodium chloride. And with further increase in temperature, this converts to zinc sulfide, which also we have studied is a sphalerite structure where the coordination number is 4. Increase in temperature, decrease in the coordination number, the structure is more open. And now what happens is, reverse on increasing the pressure. You increase the pressure, the coordination number 4 goes to coordination number 6. Further increase in temperature, coordination number 6 goes to coordination number 8. All right. Now we'll talk about, I just talked about something called order, more disordered, more ordered. What is it that we mean by it? Okay. So there is a class of phase transition, which is called order, disorder, phase transition. So once you understand this, you'll be able to visualize what I mean when I say order and disorder. Okay. So just look at this particular cube. Now this has 36 squares, okay, 18 green, 18 blue. But in this particular case, the blue and green are randomly, no, I have told you about ordering and disordering when we are talking about structure property relationship in pyrochlore and fluorides, okay. So that is what actually we mean by ordering and disordering. Just coming back to this, in this particular square, the blue and green smaller squares are randomly distributed. Okay. But if your X-ray, the diameter of X-ray is more than this, it will not be able to understand where is green and where is blue. Okay. Okay. Just keep that point apart. In this particular square, so this I call as disordered. But in this particular square, your blue and green smaller squares are arranged in a particular manner. So this is an ordered structure. Okay. So if I want to say that I want to see the square which is at, let's say, 1, 1, I know it's a blue color. If I say I want to look at the square which is at 2, 1, I know it's green color. But in this particular case, I will not be able to tell what color square I am pointing at. Okay. So what does it mean that an ordered phase is a crystalline phase of AB where A and B, they have distinct site occupancies. What do I mean by that? That means I can say with utmost confidence that that particular site is occupied only by A. This particular site is occupied only by B. But in case of disordered phase, the A and B randomize and they're distributed in such a way that you are not able to tell. So at every site, there is an equal probability of finding A and B. That is a disorder phase. So when I said the high temperature phases are more disordered because high temperature causes atoms or ions to exchange places and thus promoting disorderliness. Okay. So the low temperature phase is the ordered phase. Increase in temperature increases randomness and causes disordering. Okay. As temperature decreases, now the energy of the atoms and ions are also decreasing. If it is possible for them to adopt specific site, they will now do that at lower temperature. They will have to distinguish sublattices. In this context, in context of order disorder phase transition, we talk of something called superstructure. Okay, superstructure is actually what? Once you have had the ordering in your material, the long range ordered structure generated after ordering of A and B is called the superstructure. Okay. Now you have already studied X-ray diffraction. So you know if I am recording XRD of my ABs, let's say it crystallizes in NaCl structure. I will get some pattern. Okay. But if my A and B, they order, if they are disordered, they are whatever, it has FCC structure. But if they order, then a superstructure will be formed and corresponding to that superstructure, we will have appearance of some smaller peak. And these smaller peaks in your X-ray diffraction pattern are called superstructure peaks. All right. This next example will, make the things crystal clear for you. We are talking of brass. What is brass? Copper zinc. And this is how copper zinc actually, at high temperature, copper zinc is body center. And when do we say as lattice is body center? When the same atom is occupying the center of the cube and the same atom is occupying the corner. But here I have two ions, copper and zinc. That means the structure, the copper and zinc are randomized in such a way that my X-ray is not able to distinguish where is copper and where is zinc. So the structure looks something like this. So each atom is actually an average of copper and zinc. And because each lattice site is an average of copper and zinc, I can say that the entity which is occupying the body center is same as the entity at the corner, thus leading to a body center BCC kind of lattice. But what happens is when you cool it, this undergoes an order disorder phase transition and you get something like this, where on corners you have only copper and on body center you have only zinc. And because if your lattice point at body center and corners are different, we do not call it body center, we call it a primitive lattice. So the brass on cooling, it shows the phase transition from BCC to primitive, or in other words, upon heating, it undergoes primitive from BCC. Now BCC has got higher symmetry than your ordered primitive lattice, and this is what I mean when I said higher the temperature, more is disorderliness and higher is the symmetry. Okay, I hope it is clear now. Now these two examples are also similar. Maybe you can later on go into, just go and read it. Just that there we talked about BCC. Here we are talking about FCC. Okay, I'll not discuss it because I need to cover a little more than usual classes. So let's just come back to it if we have time, or else please write to me if you don't understand this. Okay. Now conditions for ordering. When would the atoms order? I think I once took an example of a playground. Okay. When you have all the children of same age and you just make them, stand wherever they want, it will be very difficult to distinguish between two of them. So but if there are children of class 12 and class nursery or KG or whatever you want to say, let's say 3-year-old child, then uh, it will be easier to distinguish them and they will have more tendency to get ordered. So in case of ordering, the atoms should be dissimilar. Okay, if the atoms are similar in terms of their bonding requirement, in terms of their size, in terms of their electronic properties, why would they order? They have no tendency to order. For example, silver and gold, they never order. Both are noble metal, both are same bonding requirement. They have no tendency to line up as silver, gold, silver, gold. It's all completely randomized. Also, when there is more affinity in terms of electronic attraction, bonding between A and B as compared to AA or BB, then also ordering occurs. Okay. And how does this ordering manifest in terms of characterization technique? As I just mentioned few minutes back, once the ordering occurs, you will see extra peaks in X-ray diffraction due to lowering of symmetry. Okay. And if you don't understand this, you can go back to your basic knowledge of XRD. Primitive, you have all the peaks possible. BCC, the sum of the HKL and it should be even. FC, so it decreases the number of peaks. FCC, either even or all HKL, it further decreases the number of peaks. So lower is the symmetry, more is the number of peaks. So if there is ordering, the symmetry reduces, number of peaks in XRD increase. Okay, in terms of the properties, what happens? There is an increase in ionic conductivity. We have discussed this when we were talking about the example of pyrochlores and fluoride when ionic conductivity, but I can still again talk about it. When you have an ordered material, there is an increase in ionic conductivity. Why? Because when there is an ordering, there is some kind of order in the material. The mobility of the ion, which is mobile, which is carrying the current, that faces less scattering. So mobility is higher and hence better pathways. So the ionic conductivity is more in your ordered compound. It is more malleable and ductile because there's certain kind of ordering. So making sheets and wires out of it is easier. There's better packing and the ordered phase have higher density. Okay. Now, in case of displacer phase transition, there is a particular class of phase transition which is also just talking about this because you might come across this people who would work in alloys or even in oxide. Martensitic phase transition. Okay. So martensitic phase transition is a diffusionless process. Material changes the crystal structure, that is, it goes from phase 1 to phase 2 without requiring any of the atoms to change place by more than one lattice spacing. Okay, and it happens in many metallic and non-metallic system. It can happen by applying mechanical force or by applying temperature. And one thing which is typical about martensitic phase transition is whether it was reconstructive or displacer that we were talking about earlier. There used to be a particular phase transition temperature, TC. In case of martensitic, it occurs over a range of temperature. That is, it will start at temperature T1, but it will go on till T2. Another important thing, When you go in the reverse direction, the transition will not start happening at T2. It will start happening at a higher temperature. So there is a hysteresis also. So all these are characteristic of martensitic phase transition. It is athermal. Once, suppose you have started heating it or cooling it, and the phase transition is happening, and let's say because it happens continuously, it doesn't happen just all of a sudden at one temperature. So, if you've stopped at a particular temperature, then it will not proceed. Whatever percentage has transition, it will remain like that unless now you again play with the temperature. Diffusions are small, as I told you, much less than an interatomic spacing. They retain their relative relationship. It's very reversible because it involves very slight movement. It's like, the dominoes effect of the card. It happens this way. One falls and the other falls and so on. So, in fact, it is these kind of phase transition called military transformation. They move in a very, very choreographed manner. Start from one point of the crystal, goes on to the other side. Okay, and they're very, very rapid. The name martensite was given because it is observed in steel, which has got two phases, austenite and martensite, which transforms into one another by this kind of phase transition. And hence, this kind of phase transition is given the name as martensitic phase transition. Okay, so austenite, which is actually alpha iron with carbon, steel, it is FCC. But when you quench it to the room temperature, this is your FCC unit cell. Okay. So what happens is now when you cool it, it becomes tetragonal, and once it becomes tetragonal, uh, you can see we talked about earlier also. Now this will have a smaller volume than the cubic unit cell. So the phase transition happens from FCC to phase center tetragonal. Okay, but it happens just by slight movement of the atoms, and hence it is called a. This is a martensite phase. This is a austenite phase. This is also shown in monoclinic zirconia to tetragonal zirconia. Now, this is one material which I have worked with a lot. So, monoclinic zirconia undergoes transition to tetragonal zirconia. It starts at 1000, goes on till 1200. Okay. And if you reverse it, that is, want to go from tetragonal to monoclinic, it will start only below 950. So, that much hysteresis from 1200 to 950 is observed. And then, as I told you, that it starts from one side and moves on. All of it suddenly, it just doesn't happen all of a sudden. So let's say this is austenite, and this has undergone phase transition, and at a particular temperature, this particular portion has undergone phase transition, and the regions in the nearby zone, they are still austenite. Okay, so that is why it shows hysteresis, and it happens over a. It is athermal, happens over a range of temperature. Okay, I'll talk about thermodynamic classification only if we have time. I just want to tell you about what is a metastable phase. Why is metastable phase has suddenly become very interesting? Because all of us know for any material, we will observe only that particular form at a particular temperature, which by definition of thermodynamic has got minimum free energy, okay, which we call as a stable phase. But sometimes what happens is the energy diagram of a material will have a minima, which will have free energy minimum. It will also have the local minima, where the free energy is not the absolute minimum, but it has some dip, okay. And if you are able to synthesize a material which is metastable, it has got energy corresponding to that low energy minima, it will still have some barrier to cross this and go to minima. And many a times it is possible that metastable phases, once you synthesize, they will remain there. Like diamond, it is metastable. Once it is formed, it is formed. And the metastable phases, more often than not, they show many, many interesting properties which are much better than the stable phases. So that is how the interest comes to obtain metastable phases. And that is how material scientists are, they really like to tweak their synthesis technique if they want to obtain the metastable phase. So coming to this, The metastable phases, by definition, have a higher free energy than the corresponding stable phase for the same chemical composition at that temperature. But they can be obtained if you kinetically control. If you heat it by thermodynamic condition, it will always go to this particular state. But if somehow you are able to arrest it here, then you might avoid it going to this, and the phase that you have is called metastable phase. Okay, and once formed, unless you perturb it, unless you shake it by some means, the metastable phases can be made to retain. Okay, but only if they are related by reconstructive phase transition. If they are related by displacive phase transition, it is very difficult to retain them because the activation energy is either zero or very low. Okay. So what we learned is what are phase transition, classification based on mechanism, what are martensitic phase transition. We did not study about this, but please go through the notes. It is very easy. Any problem, you may come back to me at any time. And effect of pressure and temperature on the phase transition. This is about the phase transition. We'll take a 2 minutes break and we'll come back to synthesis of materials. I will try to make it as interesting as possible. We will try to talk about in the story-like fashion. What do we do when I want a particular material? What are the conventional synthesis technique? What are the various variations that are available? Not all of them, some of them. So we'll take a 2 minutes break. Any doubt, mail me, type in the chat box, whatever suits you, but please go and refer to the notes when we take Viva. It really feels bad when we are not able to get answers, even to the simpler questions. Okay, so we break for 2 minutes. Okay, so let's now start the last lecture, the last topic rather, which is on synthesis strategies of materials. Okay. Now, why is the synthesis of material important, significant? I mean, it really cannot be overemphasized that development of the society is intricately related to advancement in the materials, and the technologies associated with the materials. And obviously, it will depend upon the synthesis of new or improvised material. So, the synthesis of the material is intricately related to the development of the society. So much so that I think we talked about in the very first introductory lecture also that even different eras in the historic time they have been made, they have been classified, they have been labeled, named based on the materials that were discovered and used in that particular area, varying from stone to bronze, iron, concrete, steel, silicon. Now we have carbon age and so on. Materials have been very important, and to be very honest, quite a few of Nobel Prizes actually went to the scientists who were associated with the technologically important material over the years. So, when we are talking of the material, first you have to synthesize the good material. An excellent material only can give you wonderful properties. So, synthesis is the backbone of materials and development associated with material. So, when we talk about the synthesis method, what are the various synthesis methods that are available? So, anybody who is like me, a conventional solid state chemist, we vouch by the ceramic method, which is also called the solid state synthesis, or in the very common layman term, it is also called the heat and beat method. Okay. Then we go to the combustion method because we need to improve upon certain properties. We'll talk about that later. Not the combustion, the soft chemical method. Soft chemical because here you don't need to apply very high temperatures. And examples are the combustion, co-precipitation, salt gel, sonochemical, micellar, hydrothermal, microwave, and so on. Then there are certain other specific methods wherein you should have a particular reactant that could be suited to that particular kind of synthesis. And in that case, you should have the methods are intercalation, deintercalation, but it can be used only for the layered material, which are susceptible to deintercalation, calation, ion exchange, high pressure synthesis, vacuum heat treatment, melt quench method, spark plasma sintering, and so on. Okay. Then processing. Once you've synthesized the material, you've got to process it. You need to obtain it in some particular forms, which could be thin films or crystal. So processing techniques are, the way you grow crystals, or if you want to get thin films, then it is inkjet printing, screen printing, and spin coating. Then people also synthesize the very interesting materials in different morphologies by using biological route. In that case, your microbes are either used as the promoter for a particular reaction, or sometimes they use as templates also. Then various ways people use microbes or the biological route for synthesis. Okay. So till very recently actually, let's say quite a few years back, materials chemistry was okay, you prepare the material, but if you prepare the material by conventional route, you'll get usual properties, which would be because they would give you the thermodynamically stable product. You'll get usual properties, usual structure, stable phases with normal dimension. But then, as the demand increased for the better material, for more interesting properties, for better efficiency, we need to now design the material. We need to design the crystal structure. We need to design the morphology. Okay? Because suppose I want to make a very dense body, I need to have very fine particles so that I can heat it and it gives me a densified body. So all this will require tempering with the synthesis. So then we have non-conventional preparation method. Either the method altogether is new, or some tweaking is given to your existing method. And once you do this, you're able to get, depending on, we tweak depending on what I need. Tailored microstructure is one of the need. Tailored properties, I want the property that suits me. Nano state, you get unusual structure, and you can also get metastable phases. And because they are unconventional phases, they most of the time yield better and superior properties. Okay, so let's talk about the very first, the age-old method and probably the mother method, which is your conventional solid-state synthesis, also called heat and beat. Why? Because we need high temperature and we need to grind, heating, beating. So the process is very simple. Once you know the compound, let's say GD2ZR2O7, and you know in what ratio I will need my, if I have gadolinium zirconate, I know my reactants have to be gadolinium oxide and zirconium oxide. And because I know the ratio of gadolinium and zirconium in the compound, that is 1 is to 1, GD2 occur as GD2O3. Already one molecular formula has got 2 gadolinium. Zirconium has got 1, so I need to take 2 moles. So once you know what is the stoichiometry that you need, we weigh the 2, 3, 4 oxides depending on what we are synthesizing. We weigh stoichiometric amount and we mix them thoroughly. Once we mix them thoroughly, we grind them. Why we grind them, we'll talk about it. Then we pelletize them. We make small pellets out of them, small or big, depending upon quantity and application. Then we heat them at required temperature for longer duration. What temperature? We'll talk about it. It cannot be any random temperature, yeah, obviously. Once we have heated it, we record the XRD pattern and we see whether our product has formed, whether it has not formed at all, or whether it has partially formed. If it has partially formed or not formed, we again break the pellet, grind them, repellet them. So heat and beat method or the solid state synthesis is actually a multi-step process, right? And also, in addition to all this, you also have to you also have to choose the proper atmosphere. When I say atmosphere, it is whether you want to carry it in the static air, whether you want to carry it under reducing atmosphere, or you want the reactive gases. That depends upon what product you want and the stability of your reactant. Then the crucible selection, because you're not just putting your material in the furnace like that, right? You need to put it in some container. So what is the material of that crucible? That is also very important. But all said and done, solid state synthesis mostly gives thermodynamically stable products. So these are some of the tools that I am a solid state chemist. I use this route day in and day out. Some of the tools that we use are a mortar and a pestle. You must have seen at your home also. Your mothers make chutneys and all that. Okay. If you want to grind bigger, like larger quantities, then we can have ball mill. Now, ball mill is a container. It has got some, the material of the container could be zirconia or stainless steel also, and then it has ball, it rotates, and the balls, movement of the balls causes the mixing or the grinding of your powders. For heating, once you have ground them, we pelletize them. I don't have the photograph of pelletizing machine, but they are like your medicine pellets. Then we heat them in furnace. Furnaces of various type. They could be tubular furnace, wherein you can heat smaller amount of sample, or you can have muffle furnace. This is a muffle furnace. It is like a box. Muffle furnace is also called a box furnace. Then these are all the material that you need to pelletize your machine. You have a pelletizing machine. Now this is a die. Okay, you put powder in it and you put this plunger and this at the bottom. So we press it and then the pelletizing machine provides the pressure. Pressure can be only from one side. In this case, we call it uniaxial. It could be from the both side called biaxial. You could just do it at room temperature. In that case, it is cold. And also while applying pressure, you can heat it. That is hot pressure. Okay. And these dyes are mostly made up of tungsten carbide, which is a non-reactive material. So the factors that affect the solid state reaction, okay, is our temperature, naturally, duration of heating, the reactants, area of contact between reactants, and the heating and cooling rate that you choose for synthesizing your material. So in general, if you understand the schematic of solid state reaction, you would be able to justify all the factors that I mentioned. So solid state process is a diffusion control process, okay? the particles have to move towards each other. And you know that for the atoms to move in the solid state requires a lot of energy. Because it requires a lot of energy, that justifies first parameter. We need high temperature. Okay. So assume this pink is your reactant A, blue is your reactant B. This is a mixture of A and B. So why do I grind? I grind them because I want them to mix. Because if they mix, there's a better probability of reaction between A and B. Okay. And then I heat them. This dark pink is the product. They have moved towards each other, and this is now how my product looks like. Okay. Now, because it is a diffusion control process, just look at this particular figure. A move towards B, B move towards A. We form a layer of product C. Now it is in the solid state. Movement is not easy. Mobility is not easy. And also on top of that, you have obtained this product layer. Now the diffusion distance is even larger. Now B has to travel even larger distance. And ditto with A. That is it. This is where this is actually the picture of this particular situation. That is why you need to again take it out from the furnace. You have to repeat your grinding so that you can break this product layer, mix them again, and then again heat it so that you get the uniform product. And this might take 2 steps, 3 steps, 4 steps. That comes from the experience. Okay. And of course, you record XRD at each step so you know whether the product has formed or not. Selecting the reaction temperature. So we know that as a diffusion control and the movement of the ions need high temperature. So what we do is, let's say I have reactant A and reactant B. Now there is something called Taman's law. Taman's law states that for any material, the diffusion of the ions, I want two reactants to diffuse towards each other, so I want them to be mobile. So Taman's law states that for any material, the diffusion of the ions becomes substantial at 50 to 70% of its melting point. It's a very rough range. Okay. And so what we want to do is, if we have two reactants A and B, we could have three ABCG, depending on what you need. We compile their melting temperature or decomposition temperature. Okay. And then what we do is, the reaction temperature is chosen as 50 to 70% of the melting point of the lowest melting reactant. If A melts at 1000 and B melts at 800, I will choose my reaction temperature at somewhere around 500 to 550. That is the thumb rule. Again, it comes by experience and doing your lab work is a lot of percentage of lab work comes by experience. Okay. Increasing the area of contact. So why do I need to grind and mix? That is because when you grind, you break the material into smaller particles. This is a bigger one. You grind it. Suppose you make 9 squares out of it. You further grind it to make even smaller square. More is the number of squares, higher is the surface area for the same volume. Okay. Higher is the surface area, more is the area of contact between your two reactants. More is the area of contact, higher is the reaction. Pelletizing again does the same thing. It compacts your material so that they come even closer, and that increases the reaction probability and also give you better sintered bodies. Regrinding and repelletizing, we have talked about, it breaks the product layer. Increasing area of contact. Now, what are the various techniques by which I can increase the area of contact? One was pelletizing. Second was, you can choose your reactant in such a way. How do you choose? We just realized that if you have smaller particle size, your area, surface area would be more, which in turn will lead to more area of contact. Take an example. I want to synthesize barium titanate. Okay. How can I synthesize barium titanate? I mix barium oxide, titanium oxide, giving barium titanate. Okay, that is one way. Suppose I take barium carbonate. Now this barium carbonate decomposes at 600, 650. I'm not very sure, but somewhere closer to that. What will happen is, when you will heat it, it will first decompose into oxides. And because it is in situ getting decomposed, it will form fine-grained barium oxide, which will have higher surface area, which will imply higher reactivity. So it is advisable to use a reactant which can in situ generate the nanoparticle of one of the reactant. Or, you make your both reactant ex situ in nanosize. There are various methods, we'll talk about it. You start with nano-sized reactant, then also the reactivity will be more. Okay. Nature of the reactant is very important once you are deciding your solid state synthesis. You have to know what is the composition because you are weighing them stoichiometry. If you do not know what actually was the stoichiometry of your reactant, you will not be weighing it properly and you will get some other product. For example, terbium. Now, most terbium is a lanthanide. Most of the lanthanide have this formula, La2O3 and then Nd2O3. So anybody who weighs lanthanide, they will what they do, okay, the formula of terbium oxide is Tb2O3 and it will weigh he or she will weigh accordingly. But the most of the time terbium oxide has got this particular formula. Okay, so you need to know what is the formula of your reactant. Also, many of the time, many a times, especially depending upon season, also if the material is not hygroscopic, your reactant might be associated with water molecules. You need to know, and that will affect the weight. So you need to know what is the number of molecules associated. You need to carry out gravimetry to know exactly how many water molecules are there. Also, when you pick up reactant from your shelves in the lab, they've been lying there for a long time. They will have occluded water, okay? They will have gases, carbon dioxide and other adsorbed gases. So that is why a good solid state chemist makes it a point to preheat the reactant before he weighs them for the actual reaction. And the preheating is done depending upon what is the synthesis temperature and the melting point of your reactant. For example, if you are working with rare earth oxide, all of them melt at, let's say, 1700-1800 above. So you can safely carry out preheating at 800. That will remove your occluded water, adsorbed gases and everything. Okay. Of course, if you need not guess it, you can run a thermogravimetry and you will know where your material is actually started getting affected. So, and thermogravimetry will also give you the temperature. Okay, this is the temperature where weight loss happened, water is gone. This is where the gases are desorbed. So, preheating temperature can also be determined by running a quick thermogravimetry test. And then, like I talked in previous slide about barium carbonate, you can choose acetates, carbonate, nitrate, oxalates. And if you're choosing them, okay, they're good because they'll give you in situ nano. But if you're choosing them, you have to be very careful about what temperature profile you use. Now, what is a temperature profile? I have to heat my material from room temperature to 1000. What I can do is I can set my furnace at 10 degrees C per minute. I can set it at 20. Good solid state chemists do not set very high temperature rate because it affects the furnace. But other than that, if you have chosen a very high heating rate due to some requirement, then if at the decomposition temperature, the temperature rate is very high, the rate of increase of temperature, it will cause violent decomposition and the material will spill out because the gases are, barium carbonate or acetate, they will evolve CO2, CO and all that. So the temperature profile has to be chosen very carefully. Selecting your vessel material in which you will hold your material. Two things that you have to remember. What is the temperature you're going to? That will decide what reaction vessel you can choose. And whether your reactants are compatible with that material. For example, a very common material that is used in solid state labs is alumina. You can go up to 1800, no problem. Recrystallized alumina I'm talking about, but they react with metal fluoride. So if you have to synthesize fluorides, you will go to platinum crucibles, platinum vessels, okay, which are inert. You can go for gold also. Okay, now platinum will react with bismuth, lead and cobalt based compound and also with the metal. So you have to be very careful. Okay, another common material that is used is quartz, but you can go only up to 900. Again, you cannot use fluorides and alkali metal. If you really need to go to very, very high temperature, the materials that are used are magnesium oxide, Y2O3, thoria or yttrium stabilizer zirconia. So you need to look into what reactants you are using, what is the temperature you're going to before deciding your vessel material. Control of atmosphere, okay? Suppose I want to synthesize a compound containing iron 2 plus. If I heat it in static air, that is atmosphere, normal atmosphere, it will be a mixture of 2 plus and 3 plus or majorly 3 plus, okay? So I need to do it in vacuum or reducing atmosphere, okay? If I need higher oxidation state, I need to heat it in oxygen. Normally, when we know our material is not sensitive, we simply do it in static air, or we can also use reactive atmosphere, that is the gases which react, but it is only in that case, these gases are one of the reactants. Suppose you want to make fluorides, okay? That is what control of atmosphere tells about. This is just one example. This is how we synthesize metal fluorides. What we do is we mix our AF2, BF2 or whatever fluoride precursor we are taking. We make pellet of it, and fluorides are very sensitive to oxygen. If you do not take care of atmosphere and heat them, they will form oxyfluorides or oxides. And then if you see, we make a pellet, cover it in a platinum foil. Okay, this is a platinum tube. I cover it with a foil. And then I put it in a glass tube, quartz tube. Okay. And then I create vacuum inside this tube. There are Schlenk lines by which you can create vacuum. Once I know that a particular vacuum is reached, I seal it here. That is why you see a sealed tube. This is called an ampule. And the ampule straight away goes into the furnace. This is how we can synthesize. Okay. Spark plasma. Now, when you are heating it in the furnace has heating elements. Okay. The current passes through the heating elements, and due to their resistance, the heat is given out and it heats up the heating zone where you put your material. In spark plasma, what we do is the direct current actually passes through the material and that creates internal heating. So that is even more efficient heating and temperature provided to the material. You get faster heating rates. You can synthesize at lower temperature and you get very dense bodies without, most of the time, when you heat the material, the particle size grows. But when the particle size grows, the density is poor. I want to have highly densified bodies, but the particle size I want smaller. Spark plasma sintering is one method that you go to because it heats so fast that it does not allow the particle size to grow and the sintering happens. Okay, so what is this? Spark plasma involves simultaneous application of high current and the pressure. Okay, so what happens is internal heating happens by Joule's effect by direct current, and it has got faster heating rate. Simultaneously, you apply a uniaxial pressure. This results in better contact between the grains, shorter reaction duration, lower temperature, and also, as I mentioned, it controls the grain growth. So this is how the schematic looks like. This is your graphite die. Die is something that holds the material, and these are the cylinders that are punched, that are pressing them together. This is how the pressure is applied, and this pulse generator provides the current. So now the material is actually heated internally, which provides more efficient heating. Okay, microwave. Again, suppose all of us have studied that some materials are microwave absorbers, aren't they? Okay, if your one reactant or both reactants or some of the reactants are microwave absorber, they will interact with microwave and they will give up and the heat will be produced. They will get heated up. This is also an internal heating method, and this can also lead to very fast heating and cooling rates. Of course, very easy. You simply have to put the microwave on and microwave off. Very fast, the material heats up, comes back. We have in our lab a microwave synthesizer where we can go to 1400 in the matter of half an hour. Okay. So, because it is easy, you simply have to put the microwave on and off. Okay. So, what happens is either the material that is holding your powder is microwave sensitive, or the material or your powder itself is microwave absorber. So, it gets heated up. And you know what is the advantage with this rapid heating and cooling thing? Advantage is now because you're doing it very fast, there is a possibility that you do not go to the stable phase and somehow your product is retained in that local minima, giving you a kinetically stable or the metastable product. You have controlled grain growth, you have better interactive bodies. An example is if you want to make silicon carbide from silica by using carbothermal reduction, which is using normal furnaces, it is multi-step and highly energy intensive. But if you use microwave, you can get the same product at 1305 minutes. Okay, that's the efficacy. Of course, every material problem has got its pros and cons. So, of course, microwave and spark plasma, they were kind of variation of solid state only because you were using high temperatures. With a normal solid state method, what is the advantage? Okay, before talking about the disadvantage, I would talk about advantage. If you want to synthesize in bulk, factories, industries, solid state is the most reliable method. Second, because you know what you have put in, the same thing will come into reactant. Impurities are lesser. But it has its own drawback. It requires high temperature because the reaction is diffusion limited. It may give incomplete reaction, and that is why you have to do it multi-step. It may give compositionally inhomogeneous product also if you have not carefully ground your material or done your multi-step heating and all. And there is a little chance of kinetical control. So metastable products by solid state is rather difficult to obtain. And you will not get the desired microstructure because you're heating it to very high temperature. The particles will grow and all, unless you're using the spark method. Okay. Solution, then what are the solutions? Suppose I want to make it, I want to not adopt the solid state. So what are the solution by which I can overcome this? Basically, why you need high temperature is because the diffusion distance is larger, right? You can decrease the diffusion distance. How can you decrease it? You make some precursor in which all your reactant elements are there in the same solid precursor. What is it? I am sure most of the people follow this technique. This is called co-precipitation. Intimate mixing of cation is required by whatever way you decide. Or you can perform reaction in the molten flux, we'll talk about it. Or you go to the soft chemical routes. Soft chemical routes generally happen in solvent, and because they occur in solvent, the diffusion distance is not an issue, and you do not have to go to high temperature. Okay. So, precursor method. Okay, what is a precursor method? Not exactly the co-precipitation. Precursor method is you choose the compound of the reactants. For example, you want to synthesize this spinel, zinc ferrite. You take iron oxalate, you take zinc oxalate in the ratio in which zinc and iron are occurring in the zinc ferrite. Okay, and I've taken oxalate, and both of them are oxalate. So once you take the solution of this 1:1, 1:1, why? Because iron oxalate has got 2 iron atom, and I need 2 iron atom only. Okay, evaporated, your precipitate will be something like this, a double oxalate. Once you've got a double oxalate, you heat it and you will get your material and the gases. This is how it happens. So you mix them, you remove the solvent, leaving behind an amorphous or a nanocrystalline mixture of cations. But it should have anions like acetate, citrate, hydroxide, which can actually be heated to give oxide. Okay. This is one example from my own work. We wanted to synthesize cerium vanidomolybdate. We took cerium nitrate, we took ammonium vanadate, and then ammonium molybdate. So my anion was vanidomolybdate. So I took the same salt of both, ammonium ion. Okay. I mixed them, I heated them at 100 degrees. Water evaporated. And once I got the precipitate, I filtered that precipitate from the water that was formed. And simply without any heating, simply at 100 degrees centigrade, I got this product. And later on, this product was utilized for sorption of toxic metal ion like lead, which showed a very, very impressive lead uptake of 100 milligram per gram in just 10 minutes. Okay. Advantages. It's a very easy, no fuss method at all. You simply have to mix. Okay. Rapid synthesis, energy efficient because you're not heating, low temperature, control over the composition because you don't have to go for multi-step thing. Limitation kya hai? What is the limitation? Now the reactants have to be of comparable solubility. If they have different solubility, would precipitate and one would not, or they would not precipitate in the stoichiometry that you have measured. Trace impurities, if present in your reaction medium, also get incorporated. Not much control over particle size. And then heterogeneous particle size and batch-to-batch reproducibility, because trace impurities issue is there, that might be there. Sol gel. In sol gel, suppose I want to synthesize this multi-component oxide. Okay. So what do? I start with the alkoxides of this. Now this is basically the only thing is it requires your organic agent. So what you do is, I'll show you here. You mix them together, okay? And then what happens is after mixing them, you carry out the hydrolysis. This is hydrolysis. Your alkoxide linkage with water will form hydroxide. And then what happens is third step is condensation step. All the hydroxide, MOH with MOH or MOH with MOR or MOX, it will lead to evolution of either H2O, okay, or XOH or whatever, and you will form MO, three-dimensional network, which is called gel. Okay, this is sol and this is gel. This is why it's a sol gel process. And once you've got this, you heat it at high temperature and you will get your desired product. Control of the particle size as well as the product will depend upon how better you can control the salt step and the gel step. So methodology, you mix them in the liquid phase, carry out hydrolysis and polycondensation, okay, and then after various processes such as drying and sintering, materials with microstructure and even nanostructure can be prepared. Again, parameters that affect your product properties, rate of hydrolysis, rate of condensation, okay. If you can really carry out the hydrolysis at slow and controlled rate, you can get smaller particle sizes. Advantages, because you're mixing them all in a solution, right? So the products are homogeneous. They're high in purity. You can control the powder properties, porosity, particle size, okay? Low temperature synthesis, then allows for the fine control of the chemical composition. So if you want to make 3, 4, 5, 6 component containing oxide, this is one of the best methods. Enables smaller quantity of dopants also to be introduced, and then it can be dispersed. Problem, longer reaction time, and you have to employ, because you're taking alkoxides, you need organic solvents. And that is why, it's better to do things. Otherwise, organic solvents are not an issue. That's not a problem. Just that aqueous is a little more safer and better and easier. Okay. Hydrothermal. Hydrothermal is how your pressure cooker works. Okay. So what we do is we actually put our material in the water because it is hydrothermal. If you're taking any other solvent like alcohol or something, we call it solvothermal, but it is same. You put your reactants, they need not be soluble, okay? Or they could be partially soluble. And then you close the container tightly and then you heat it above 100 degrees centigrade, which is the boiling point of the water. But because now you're also increasing the pressure, the boiling point is the temperature at which your internal pressure becomes equal to the external pressure. Because you're increasing the temperature, pressure, the water will not boil at 100 degrees and we heat it up to 160, sometimes 200. People also do it 300, but 160 to 200 is a most common hydrothermal temperature range. Okay. So the synthesis is performed. Heterogeneous reaction means because they need not be very soluble. In the aqueous medium at temperature above 100 degrees centigrade and pressure above atmospheric pressure. Okay. So what does water do? It's a reaction medium. It transmits the pressure and it is good to have soluble, but in this case, if they are not completely soluble, then also it is fine. And we know that many materials are either partially soluble in water under pressure. So it aids in reaction. This is how your hydrothermal setup looks like. This is the autoclave. this is a liner. Generally, it is of Teflon, and you put your reactant in it, close it, and then heat it for, that duration and temperature mostly is decided by the kind of reaction that you want to carry. Also, the pressure that would be generated within your autoclave when it is heated under the airtight condition in your furnace or oven or in hydrothermal setup, which are specifically designed for that, it will also depend upon the filled volume. Okay, so we have to be very careful with that. Okay, so beauty of hydrothermal material, hydrothermal is actually the process that the nature follows. The crystal, the material that are observed in earth crust, they have been actually being formed in the earth crust under the wet and the high temperature condition. Not very high temperature, kind of the temperature that we work in hydrothermal. So it gives defect free material, and the hydrothermal gives very, very interesting morphologies. And there is a probability of obtaining metastable product. Advantages, there are some crystalline material which you would want to synthesize, but they are not stable at high temperature. For example, cerium silicate. Now it is stable only up to 425, whereas ceria and silica both need high temperature if you want to make this material by solid state. So you heat them at 800, cerium silicate will never form because its decomposition temperature itself is 400 something. So you can synthesize crystalline phases which are not stable at high temperature. Material with low melting point, high vapor pressure can be obtained. And the beauty is it can create larger size, defect-free, high-quality crystals. Controlled morphology and metastable and difficult to synthesize phases can also be obtained. Limitation is you need autoclaves, and because it involves water or solvent under high pressure, it has to be monitored. Okay, there's nothing, no problem. People carry out hydrothermal everywhere. Just that, which otherwise is also true, whenever you are in lab, you have to be very, very careful and alert, whatever work you are performing. Multi-component material could be an issue by hydrothermal thing. But this was one work that we did in our lab. We wanted to synthesize this layered compound. We started with zinc carbonate, ammonium vanadate, mixed them. I got a yellow precipitate. Then I put it in a Teflon container, autoclave, heated at only 120, not more than that, for 6 hours. Okay. And here actually I varied the duration also to see whether I'm getting the product or not. The beauty was even 15 minutes of autoclaving was giving me the product. But why did I heat it at different duration? Because you see the beauty of the crystals that I'm getting. These are the SEMs. This is how the product looked at 15 minutes. After 13 minutes, it formed these hexagonal platelets, which were very beautiful, thin, transparent platelets after 2 hours. And after 5 hours, they started getting damaged. So we did many of the study as a photocatalyst or something with this particular product, which was the best quality product after 2 hours. And we got some very interesting results with this. Okay. I don't think I will be able to cover all the techniques, but whatever we can. Sonochemical is again a very, very interesting technique. What happens is, this is how a sonochemical setup looks like. Okay, this is your cooling bath, and this is the sonochemical setup. You have your material dissolved in this bulb in water or whatever solvent you choose. And with the help of this titanium horn, it is actually made to vibrate, and that frequency is controlled by this power supply and transducers. Okay. And these sound waves, they create some kind of hotspot in your water. And these hotspots, which are also called acoustic cavities, they act as small reactors wherein the reaction happens. So why these acoustic cavities, the reaction is possible? Because for a very small duration of time, that we can get high temperature of the order of 5000 Kelvin, the pressure greater than 1000 atmosphere. And because it persists for a very, very small duration of time, the heating and cooling rates are very fast. And because of this, the reaction happens. You can get metastable product. And what is the beauty is, outside the temperature is ambient, right? So it permits synthesis on a bench top in the room temperature liquid. that would otherwise require very high temperature, high pressure, or longer reaction duration. Then sometimes what happens is the product form inside that hot spot or the bubble. In that case, it is called primary sonochemistry. Sometimes the radicals or more active species are produced in the radical bubble, which move out and they react with the other reactant to give you the product. In that case, it is called secondary sonochemistry. One example of sonochemical reaction, we wanted to synthesize indium oxide for optical application. We started with indium ethoxide, used this as a hydrolyzing agent as well as a capping agent. Put it under the sonochemical condition, we got indium hydroxide. And this is the TEM of indium hydroxide. Nice cubes were obtained. Heated them, we got 9 nanometer size of indium oxide particles. Very, very simple synthesis. Of course, you can extrapolate it to complex oxides. And then it was used as a white light emitting material. Advantage, nanomaterials at ambient temperature. Reaction rates are very high. You need very less temperature. Quick and simple. You sonicate for 30 minutes in the slots of 10 minutes. Various shapes can be obtained. Limitation. If you have a heat sensitive material, then it will be difficult because it cannot withstand acoustic cavitation. Scaling up is a difficult issue. You can do lab scale, but scaling up at, when you want to make it at the industry level, factory level, or let's say few kgs and all that, that also is difficult. Also, energy supply needed to carry out sonochemical is quite high. Therefore, it is energy intensive. So even though the yield is high, the yield per unit energy is low. That's a problem. So it can be used for interesting solid state material science that you can do. But of course, it has its own limitations. Okay. So now we are left with metathesis, molten flux, and gel combustion. I'll tell you about the flux method. It is important. Flux is nothing. Solid state had a problem that your ions had to diffuse. What if I provide them a material, okay, and still carry out the solid state only? So what we do is, like we did in solid state, we take our reactant in stoichiometric amount, mix them, grind them. Now we put them in a flux. And that flux is a eutectic of two salts, or it could be a single salt also, which melts at low temperature, 500, 600. And then you put your powder in that flux. Okay. Now you heat it. You don't need to go to the reaction temperature at which your reactant, what we were talking about, 50 to 70% of the lowest melting oxide. No. Simply go to the temperature slightly above the melting temperature of the flux. Now this flux acts as a swimming pool in which your reactant particles are there. They're not soluble, they're still solid. But now the diffusion problem can be controlled. Okay. So we use salt. Flux salts are used as flux. They melt much below the reaction temperature. Reaction can be carried out when your salt is molten, enhances diffusion, lowers reaction temperature. Now, once the reaction is carried out, you need to separate it also, no? And the beauty is your flux is water soluble and your product is not. You have to carefully choose flux route only when this is the condition. So once your reaction is over, just wash it with water. The flux will go and your product will remain. Okay. So you weigh the flux salt, you grind them both together, both the powder and the flux, and then heat the temperature greater than the melting point of the salt or the flux. Let the reaction cool and wash off the flux. So what are the different kind of flux that are employed? I said water soluble, sodium chloride, eutectic of NaCl, KCl, eutectic of NaOH, KOH. Why eutectic? Because if you remember your thermodynamics, if this is your reactant A, this is your not reactant, material A, material B, and if they form eutectic, this is the melting point of A, this is the melting point of B, this is the melting point of eutectic. So eutectics have lower melting point than the constituent salt. Okay. Just one example, I tried to synthesize, this is a very old work that I did in my MSc, tried to synthesize this compound with the flux, NaCl, KCl flux. So this XRD is when I did by solid state, this XRD is when I adopted the flux route. Solid state only, but in flux. I got single phasic product. This one had impurities. Okay, and not just that, this is how this is how the morphology looks like. This is solid state, not very clear grains, and this is the one that we obtained by flux route. Okay, problem is sometimes the ions of the flux can get incorporated in your material. How can you get out of it? Choose a salt that has cation or anion present in your product that you want. For example, if you want to synthesize this, now this is strontium. Choose SrCl2 flux. Okay, common ion. So even if it goes, doesn't really matter. Or you use the flux where the cations are much different in size than your reactants. For example, you want to synthesize this. Both lead and zirconium are bigger ion. Choose B2O3 flux. Boron is very small. It won't go into your material. Okay. High pressure, all of you know about it. Combustion is one synthesis which we do routinely in our lab. And I kept it at the last because I wanted to discuss more about it. But now I think I will only give you the gist of what the combustion synthesis is. Combustion is creating fire, right? But here we create the fire inside our beaker. How can you create a fire? When you want to put up a fire, put on a fire, you need oxidant, you need fuel. And this is what we utilize in the combustion synthesis. Okay. So what we do is we take our reactant as nitrates. Now nitrates are oxidants. Okay. Which are, and we take some amino acids like glycine, urea, citric acid, they act as fuel. They're very cheap also. What we do is we dissolve our oxides. For example, I want to make Nd2Zr2O7. I will take Nd2O3, ZrO2, zirconium oxynitrate, dissolve it in very dilute nitric acid. I'll get nitrates. Okay. And then I put my fuel also in that. Of course, there has to be a certain ratio, which is calculated by the propellant chemistry ratio. The fuel goes into the, now suppose the fuel was not there. I had only my zirconium nitrate and Nd nitrate. Now if you evaporate it, at the end you will get only powders. But if you have your fuel in it, now these fuels are bidentate. They will hold on to the ions. So what will happen when the water is evaporated, because they're holding on, they will form a gel kind of thing. Now what is the advantage of this? A, they've held on to them, forming a gel. B, now Nd and zirconium are also close by. The diffusion distance is reduced. Okay. Once you get the gel, this evaporation is done very slowly. We get very nice gel. And we do it on hot plate. You can do it in furnace also. And we suddenly increase the temperature from 80 to 100 to 300. Okay, hot plate maximum temperature. It shows combustion. For that fraction of second when the combustion is going on, the temperature rises depending on the fuel, nature and quantity. It rises to as high as 1400, 1200, 1300 for a fraction of second. In that fraction of second, either you get directly your product or you get the precursor to the product which can be heated at lower temperature to get the final product. This is what combustion is. So you get instantaneous high temperature generated for very short duration of time. Requirement, you have to have very clear metal salt solution. That is the requirement. You cannot go with the partial solubility in this case. Okay. This is how clear picture. This is the gel. Okay. And this is the combustion is being carried out in the beaker. The powder property that you will obtain will depend upon what is the fuel you are using and what is the quantity of your reactant to the fuel. Please go through these notes. These are very, very self-explanatory. Unfortunately, I'm not able to cover them in detail as much as I would have liked to. But go through this. This is one technique. Those of you who are going to follow material science is actually going to be benefited by this. Okay. Now, just a comparison. This is the Nd2Zr2O7 synthesized by solid state, and this is by gel combustion. You get nice, very defined grains. Okay. This is cerium oxide obtained by making hydroxide and heating, by oxalate and by gel combustion. So the morphology that you're observing is clear indication of difference in the product that you can get. Of course, there are many advantages. Will not cover it now. Ion exchange will have to skip. Okay. Right. So what basically we tried to cover is, we of course cannot doubt that creating anything is the most fascinating thing, and it's also one of the most fascinating branches of science. Synthesis route, any synthesis route you take, that will have its pros and cons. But you have to know what you want, how you want, in what form you want. That will decide your choice of synthesis route. If you want the most reliable route for bulk production, phase purity, and you want a thermodynamically stable product, you don't want it to change phase during application, go for the high temperature route. Shimizu, which is a name for soft chemical route, can give you metastable, can give you nanomaterial. You can have morphology control, you can make nanorod, nanotubes, whatever you want. Depending on what you want, you have to choose the best possible soft chemical route for you. You have to have proper reactants and reaction parameters. And then, basically, all the story about advanced functional material revolve around endeavor, struggle to control morphology, powder properties, and the crystal structure. This is where I would want to end today's lecture. We had interesting 6 sessions, and now please go through your notes. This was the very basic part of the solid state chemistry that I covered. Any doubt, feel free to write to me anytime, and I wish you all the best with the rest of the course. Thank you.